Alright, so I'm just going to go a little faster this time. It's important to know that if I'm going too fast, you can actually slow down YouTube videos. Just Google slow down YouTube videos. If I'm going too slow, you can also speed me up. So check that out. That's a feature that a lot of people don't know about. Alright, so if I have 2.52 gram piece of magnesium, and I'm putting it into a beaker of 125 milliliters of acid. So the first thing I want to do is write a balanced reaction. That's almost always the first thing I have to do all the time. I know magnesium's a metal, so that's probably a solid. HCl has to be aqueous because it's an acid, and also it says molarity. This is going to be a single replacement reaction because of the simple fact that I have an element and a compound here. So I'm going to take the Mg and buddy it up with the anion out of the HCl, so that would be Cl. That has a -1, and Mg can only be a +2, so I have to have 2 of those. Chlorines are always soluble except for when with silver, mercury, and lead. So I'm going to put it aqueous there. And then the other thing, so hydrogen is going to become an element, and hydrogen is a diatomic element that happens to be a gas. So that's going to look like that. I need to put a 2 there because I need both 2 hydrogens and 2 chlorine. So there's my reaction. Oh, it wants to know the mass of hydrogen gas. So I'm going to start with magnesium, not for any particular reason. You could start with HCl as well. You're going to do both of them because you have to figure out which one's limiting. We're given amounts of both of them, and it's unlikely that they're the exact right amount for each of them, so we got to figure out which is the least amount. So the weight from the periodic table, I don't have the exact copy, you guys do on this computer, so I'll just use the internet, but magnesium is 24.305 on here, and so that number is grams per mole, but in this case I want to put the grams on the bottom so that it will cancel and I get moles from that. When I enter this into the calculator, I'm putting in 2.52 divided by, because the 24 is on the bottom of that fraction, so that makes it a denominator. So from that we get that there were 0.104. It actually says 368, but I'm going to round because I only have 3 figs. I could keep 1 extra if I wanted to be really diligent. So there's that many moles of magnesium. I'm trying to get to moles of hydrogen to get the mass of hydrogen gas. So in order to do that, I'm going to use that molar ratio, which comes from the balanced reaction. So it's the relationship between magnesium and hydrogen here in this case. So there's 1 hydrogen for every 1 magnesium. Mathematically it doesn't change anything, but it's very important on the unit because it gets rid of magnesium. And it's looking for mass of hydrogen, so I'm going to use the atomic weight of hydrogen, which of course is 2 times 1.01 grams for every mole. Okay, so the final answer here is 0.209. Now in my calculator I actually kept all the extra significant figures. If you don't, you might get a different answer. That's not moles, it's grams of H2. So that's how much H2 the magnesium could make. We have to consider also how much H2 might come out of the HCl. So this is a little bit different because we're starting with 125 milliliters of 1.5 molar. As we discussed in class, of is a mathematical phrase that has very specific meaning. It means multiply. So kind of just the way I was thinking of the problem is there's 125 milliliters of 1.5 molar HCl, so I'm going to multiply those together. But I'm going to transform the big M into what it really is. So moles is on top and 1 liter is on the bottom there. That's what that big M means. Molarity is moles per liter. Specifically moles per 1 liter. Don't get it confused. You can't put 125 milliliters on the bottom because that doesn't work. It's defined already as 1.5 moles per 1 liter. So we're going to keep it that way. And so I noticed that the liters and the milliliters aren't quite the same thing, but I know that there is 1,000 milliliters for every liter. And I decided to put the milliliters on the bottom so that they'll cancel with these milliliters. And then I'll get moles out of doing that. So in the calculator we go 125 times 1.5. And I get 187.5 from that. And divide that number by 1,000 to get our final number of moles. This is HCl. Now, to figure out how much hydrogen can be made, I'm going to use the relationship from the reaction. So there's 2 HCl's for every 1 hydrogen. And the weight here is going to be the same as before because it's still H2. So I'm going to take that 0.1875 and divide by 2, and then multiply by 2.02. So basically, we get almost the same exact answer. It's 3 sig figs. My calculator says 0.1893, so I'm just going to say 0.189 grams of H2. Okay, so now the trick is only one of these two things can be true, and it's going to be the one that is lower. You can't make more than 0.189 grams because you don't have enough of the hydrogen to do it. So the right answer here is that there is 0.189 grams of hydrogen possible, and the limiting reactant was the HCl because that's what we ran out of. Okay, so if we produce 0.189 grams of H2, the next question says how much volume would that occupy? I'm going to do this one in a purple color, I think, so that you can see it. So we're starting with the amount, 0.189 grams, and they give us a density. Density is a conversion factor where I can go liters on top, grams per 1 liter is what that means, and put the grams on the bottom, so that would cancel. So to figure out how many milliliters, I'm going to have to do one more step. It says milliliters right in the problem, so I'm going to use what I know about the metric system here. So 0.189 divided by 0.12, and then multiplied by 1,000, and that'll be our volume of the gas. It's a relatively small number of moles, but gases can occupy a lot of space, so don't be shocked if it's a big number. 1,578, but I'm just going to write 1,580 because we only have 2 sig figs, or 3. So it's quite a good size, more than a liter. Okay, so number 3 we did do in class, but I'm going to run through it again just in case you want to see it again. Oh, not this number 3, we did a different number 3 in class. So for this one, we are given some information, and almost everybody tried to do this problem, but was having a really hard time with it, I think, because realizing that you can have a delta H of combustion, which is what this is referring to, that isn't kilojoules per mole is a possibility. So anyway, so combustion of sucrose, so it's C12H22. So we're going to start by writing the reaction. It's a solid because it's sugar. And, combustions always require oxygen as a reactant, so I'm going to put that right in there. Again, you can't have any barbecues in space, guys, and X-Wing ships don't actually blow up the way they show it. Okay, your products of a combustion are CO2, which is gas, of course, and water. And I'm going to assume this is going to be a gas as well, only because it's, burning, it's on fire. Alright, I like to balance carbon first. So here's carbon, we have 12 on this side. I'm going to make it so I got 12 on that side. In this example, I'm going to do hydrogen next because it occurs only in one place in each side. So here we have 22. Over here I've only got 2, so if I put an 11 in the front of that, I have 22. Last, oxygen. So I got 11 over here, plus 2. I imagine that's probably going to change. And then over here, 12 times 2, so that's 24. Plus 11 more. Okay, so 24 plus 11, 35. Now, over here I've got 11 already and only 2 more. So what I really need is 35. So if we just go 35 minus 11 that I already have in the sucrose, we need 24. Okay, so if I want 24 I'm going to have 12 of those, I think. Right? So it would be plus 12 times 2. So 24 plus 11 is 35. So now that checks out. Okay, so that's our balanced reaction. I am going to erase the extra stuff here, but that's how I like to balance. I like to make kind of like a little chart here to keep track of the reactants and the product side. If you learned a different way, but it works for you, that's fine, just as long as you get a balanced reaction. And I can kind of understand a little bit about how you're approaching it. It's fine. Okay, so the next question is to convert that value, 3.87 kilocalories per gram, to kilojoules per mole. So right away, the first thing I'm going to do is make this fraction vertical. We don't always write the number on the per part, but it means per one of them. I want to get to kilojoules per mole, so I guess the first thing I'm going to do is go from kilocalories to calories, right? So there's 1,000 calories in 1 kilocalorie. Okay, and then I have to remember how many joules. It's 4.184 joules for every 1 calorie. So that gets rid of calories and kcals. And I got to get it to kilojoules. Kilojoules are big, so there's going to be one of the big thing and 1,000 little ones. So that'll be kilojoules. Now grams is different because to get rid of grams and get moles, I have to have a molar mass. So I should probably show that work in case I mess it up so I can get some credit for the problem. It just takes a second to show it. It's not that big a deal. Okay. So this ends up being 342.34 grams per mole. A lot of you are still in the habit of saying that that's 342.34 grams, and then you get lost in the math. It's not just grams; it's grams for a mole of that substance. And so I'm going to use that where I put. Ignore that. That's supposed to be 2. Where I put grams on the top and moles on the bottom because that'll cancel these grams. Okay, and it'll get us into kilojoules. So basically 3.87 times 1,000 times 4.18. I'm going to go times 342.34. That equals a giant number, and then I'm going to divide by 1,000. So I'm kind of canceling out, actually, numerically, these two. So you don't even have to really do that mathematically if you don't want to. The answer is 553.70. Oh, the points don't matter actually because there's only 3 sig figs, so I'm going to round it anyhow. 3 sig figs from here. So, I'm just going to go 554 kilojoules per mole. Okay, so that is the delta H of the combustion in this case. 554. Oh, it's going to be negative because it's a combustion that always produces heat. So, ta-da! It's going to be releasing it. And then it says write the heat of formation reaction for sucrose. Okay, so heat of formation reactions are from the elements that make up the sucrose, and it's going to produce 1 mole of sucrose. Okay, so in other words, when we look up the value of sucrose, the delta HF is if you make just 1 mole of that. It has to be from elements, so carbon, and specifically we're going to choose graphite. There's many different kinds of allotropes of carbon, but graphite is the one we're going to use here because it's the one that has an enthalpy of 0 in the appendix. The elemental form of hydrogen is H2, so we're going to have 11 of those. And oxygen's funky because it's O2, and this is an odd number. So you're actually going to get 11 halves of O2. That would be, of course, 11 atoms. And we are aware you can't have a half of an atom, but this is how you have to write the formation reaction. Some people go through the whole process where you get to here and you say, okay, well, I can't have a fraction, so I'm going to just double this guy. Okay, so if you do that, then it would be 11 here, 22 here, and 24 here. And that is technically the balanced reaction, but it's not a heat of formation reaction because that has to specifically form only one molecule. Okay, so this is the best one. Sometimes when I'm doing these, I write the balanced reaction properly, and then I realize, oh, I gotta go back and divide everything by 2 to get the heat of formation reaction. Okay, so it says determine the heat of formation of sucrose. So basically, we want to know how much, heat this reaction requires. And so the trick is to use this combustion for our benefit. I'm going to erase all of this so I have room to work. Okay, so in the appendix, I go and look, and we're not going to find this because that's what the question is asking us to solve. Oxygen's going to be 0 because it's an element, and then I can look up the values for carbon dioxide and water. So let's see, we're close to water first over there. That one, we decided this was a combustion, so negative 241.82 is what I'm going to use. And then for CO2, we looked at this earlier, but it's negative 393.5, I think. Yep, there it is. Now, when we're assigning our delta HFs, I'm not going to be multiplying yet. So we're going to go products. So that's 12 times negative 393.5 plus 11 times negative 241.82. Products minus reactants. Well, 12 waters is easy, or 12 oxygens is easy. And we have one of those, and we don't know what that is. We do know that the delta H was negative 50, what was it? Negative 554 kilojoules per mole there. So, since we know the total heat of this reaction, the total enthalpy here, and we know all of these variables, the only thing I don't know is how much sucrose is. So now, once you've got it to this point, most people can solve this. We don't generally have a big math issue in this class. Okay, so we end up with a negative, really big number, minus x, because minus 0 plus x, so just minus x, really. And I guess I'm going to add this number to both sides. I think the number that I get is negative 6,000, or is positive 6,828.2 over here, and that equals negative x. So x is going to be the negative of that. Technically, that would be our last number, so negative 6,830 kilojoules per mole of sucrose. That is a lot of energy, which is why we like to eat it. Okay. So, bond enthalpy was moved to chapter 8, I discovered in this edition of the textbook. They have the same information, it's just that they've moved it around a little bit. We're not going to cover this on this exam. We will cover it with the chapter 8 material, which means we can't answer F. Okay? But just keep that in your hat. We'll get back to it. Don't worry. Alright, so here we have specific heat problem. There's a few ways to approach this. The way that I like to do it is to minimize the number of times I have to do the same calculation. Specific heat problems are MC delta T, and the C is the specific heat. And everything has its own specific heat. Like, for example, we know the specific heat of water is the 4.184 joules per gram degree C. Okay, so here we're trying to figure out, based on some data, which of 3 substances were being tested. The mass of the unknown is right here, so I'm going to plug that in for M. It says that 1.47 kilojoules of heat, so Q is heat. Usually we see that in joules, so I'm just going to go ahead and jump on that right away, because joules per gram degree C is the units for our C values. So I'm just going to go ahead and do that. Then it says that the temperature was changed, it was raised by 36.5, so that means it's a positive delta T. 0.4. So now we can plug everything in. So Q of whatever it is, the Q equals 1470. I don't need to rewrite the equation. So we're just going to go 1470 joules equals 19.70 grams times whatever the C is, we don't know, times 36.4 degrees. Now you could rearrange this first, in which case you'll kind of know if you did the setup correctly or not, because you're going to get that weird unit where you have joules on top, degrees, and grams on the bottom. Alright, but that's going to be our heat capacity here. And I'm not being super diligent about it, but the bottom has to be multiplied together first before you can answer this question properly. So my calculator says 2.04998, but I think we just have 3 sig figs because of the temperature. In calorimetry problems, it's almost always temperature that limits you. None of these units cancel, so we keep them all, which is good because that's the funky units that we expect from heat. And so if my value is 2.05, wait, what did I write? Whoops, ignore that. 2.05 joules per gram degree C, then it must have been acetic acid. So on these kind of problems, you got to make sure that you actually answered the question. Otherwise, it's really easy to just solve for the C and move on, right? But the question isn't asking that. It's asking which of the 3 substances it is. So it has to be acetic acid because that's our closest value there. Okay. So we have a lump of chromium. Its mass is, so I'm going to just make a column here for the info I have about chromium. The main problem with calorimetry issues, the main issue with calorimetry problems rather, is in organizing the information. So tables are really helpful for that. So mass of the chromium is 95.3 grams. And let's see, a temperature of 90.5. I don't know if that's final or not, so I'm just going to put T. Oops. 90.5. Put it in the calorimeter. Oh, that sounds like an initial temperature for the metal because we just put it into the instrument that we're measuring it with. The calorimeter has 75.2 milliliters of water, so this is going to be about water. I need a mass. So right away I'm looking for a density because, oh look, there's one. Here's the density of water at that temperature anyway. So 0.9987 grams per mole. So I can right away just go. Most of the time we assume that the density of water is 1 unless proven otherwise. Since those two problems are like very close in proximity, I'm just going to go ahead and assume that the density is probably the same. So we find out that there's 75.102224 grams. I'm just going to put 0.1 grams. So now that's the mass of water. Let's see. Oh, the water starts at 20.5. So when the metal is put in there, it's at 20.5. The metal is really hot, so it's going to get hotter. And the mass of everything together is 28.6. So that's our final mass at the end. When objects are touching the water, the calorimeter, and the metal, they are all going to equalize their temperatures. Heat keeps moving around until the temperatures are equal. So we can find the specific heat. So here's another way of doing that same kind of problem. I'm going to rearrange first. So I'm going to divide by m delta T on both sides. So the heat capacity is Q divided by m delta T. So the thing is, if I can find the Q of the metal, I have the mass of the metal, I can find a delta T right here because it's final minus initial. this will be a negative number because, of course, the metal is cooling off. So I expect it to be a negative number. Please, please, please resist the impulse to turn that into a positive because, of course, you can't have a positive temperature change for two separate objects. That won't work. Okay? So if we can just find the Q here, we're good. And the secret is that the Q of the water is equal to the opposite of the reaction. So here, we'll do a delta T as well. Okay, and so now we have a mass, we have delta T. Oh, and then we also know the heat capacity of water because it's a constant. So I can just go the mass, 75.1 grams, I think that was grams, yeah, times the heat capacity that we already know and love, or at least we tolerate it, times the temperature. Okay, so this whole thing will give us the heat of the water, which was absorbing the heat from the metal. So in an indirect way, we're kind of calculating the heat of the reaction ultimately. So the heat of the water is 2,545. Grams are going to cancel, and degrees Celsius, so that just leaves joules. So now I know that the heat of the metal is the same thing, but with a negative sign. And so the heat capacity would be negative 2,544 joules divided by the 95.3 grams and negative 61.9 degrees C. Now heat capacities can never be negative. That would mean the object is giving away heat that it never took in, which of course violates our rule of conservation of energy. But the negative on the bottom cancels with the negative on the top, so it's actually not a problem anyway, as long as your temperature is actually going down. If you had it backwards, that wouldn't work. So we have a heat capacity of 0.431 joules per gram degrees C. Okay, so here we have a very similar process to what we had in lab, right? So if you've already done the lab calculations, you have kind of an advantage on this one. We're taking a volume of water that has a density, so I'm going to use that density again to get to the number of grams for the water. And then I need to know the mass of the entire reaction, so I'm going to take that and I'm going to add the weight of the NaOH, 1.45, and that'll be the weight of our total solution, so that's going to equal M. So the mass here is going to be 101.32 grams. Okay. The initial temperature of the water is 20.1 and the final is 24.1. Oh. Yeah. And again, the heat capacity of water is known, right? So our mass is 101.32 grams. Our heat capacity is always the same because it's water. And our delta T here is going to be final minus initial, so 24.1 minus 20.1. So that'll be 3.0 degrees C. Don't forget that that is a significant figure. Otherwise, you end up with only one sig fig, which is basically there's no purpose in doing an experiment with just one sig fig. It doesn't give us any information that we didn't already have. So we get 1,271.7 out of the calculator. I'm going to go ahead and put just 2 sig figs because the temperature has 2, so it'll be 1,300 joules there. So the Q of the reaction is going to be the same thing but opposite. Okay. And it tells us to calculate it in terms of kilojoules per mole of water formed. So to figure out how many moles of water are formed, I'm going to base it on the solid here. And the reaction that's occurring is just oh, it's not going to be per mole of water, it's actually going to be per mole of NaOH. But anyway, so we have 1.4 grams of NaOH, and we have to use the molar mass. So it's going to be grams per mole, and I'm putting moles on top so I can cancel the grams, right? And so it ends up being 22 0.99 plus 1.01, so that's 24 plus 16. Right, so it's basically 40 grams per mole. You could do more sig figs if you wanted, that'd be fine. I think it's 39.98 or something like that. But you get pretty much the same answer. So we're going to go 1.45 divided by, because you know the 40's on the bottom there, 0.03625 moles. Okay, so I can go up here, and it's got to be kilojoules, so I'll do that first. So that's negative 1.3 kilojoules. And then we're going to take our number of moles and just divide it, because the unit is kilojoules per mole. I would say like 95% of these problems you can do with almost no chemical knowledge if you just know how to follow your units. Okay, and so that's the importance of units here. So what we get is negative 35.86. I'm going to keep my two sig figs up, so it would be negative 36 kilojoules per mole. Okay, that's it for the first side. I will also upload the second side soon, so you can study that as well.